All right, 3.8. Use inverse matrices
Inverse. I don't know a word I like to see.
to solve linear systems. So an identity matrix is an n by n matrix or is a matrix, well, it's an n by n matrix that has ones on the main diagonal. I'll show you what that means in just a second. And zeros everywhere else. It's denoted with an I. So if we had matrix A times the identity matrix, we would get out matrix A, and if we had the identity matrix times matrix A, we would get out matrix A. Okay, remember, it does matter what order when we are multiplying, okay? That can change things, so just keep that in mind. So the identity of a 2 by 2 be 1, 0, 0, 1. So this is the main diagonal right here, okay, where the ones are. If I had it for a 3 by 3, be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and that can go all the way out if you had like a 10 by 10. Okay, the ones are always on the main diagonal, and then zeros everywhere else. Two matrices are inverses of each other if the product of each gives the n by n identity matrix A times B is equal to I, and B times A is equal to I. Okay, it would have to be true both directions for it to be truly inverses of each other. Now, the only inverses that I'm going to require you to find are going to be for 2 by 2s. You can find them by hand for 3 by 3s, 4 by 4s, okay, whatever. But it just takes a long time, so anything bigger than a 2 by 2, I'm going to let you use your calculator to find the matrix. Okay, just remember it does have to be a square matrix. So if you have like a 2 by 3, you can't find the inverse of that. And then we'll also go over how to solve a linear system. Actually, not by inverses. I'm going to show you an easier way. Since I would basically be letting you use your calculator either way, it makes sense to show you the easier way to do it. So the inverse of a 2 by 2 matrix the inverse of matrix A is A, B, C, D, or sorry, that being matrix A, is A, and we raise it to the -1, that symbolizes that we're taking the inverse, is equal to 1 over, okay, the determinant of A, so we're putting it in like the absolute value bars. Remember that represents that we're taking a determinant. And this is where it gets a little bit interesting, okay? We take matrix A and we swap A and D. So on that main diagonal, we're going to swap them. So it's going to be D in the top left, A in the bottom right. B and C stay where they are, but they become negative. Okay, or they change signs. So if B was already negative, it's becoming positive. Okay, it's changing signs. So negative B and negative C. So it would read across D, negative B, negative C, A. So what you have is 1 over AD minus BC. Okay, and remember, when you take the determinant, you're taking it of the actual matrix A, not this changed thing. And then times D, negative B, negative C, A. Okay, so all this is doing then is you're multiplying by a scalar. You're not multiplying two matrices together. And this is obviously provided the determinant of A is not equal to 0.